Hello, my name is Aiden Rosenkrantz. I'm a mechanical engineer here at Purdue University, and I'd like to tell you a little bit about my research. To start off, we'll go through an introduction which will tell you a little bit more about what it is we do and what exactly inspired us. And then we'll walk through the methodology which will explain the preparation of electrode cells, the accelerated aging process, the design of a printed circuit board, and the experimental design of our project. And then we'll walk through some results and explain exactly what those mean, and we'll talk about some conclusions that can be drawn and what we hope to achieve in the future. To start off, bioelectrodes are the future of modern medicine, enabling us to interact with certain nerve and muscle impulses. These electrodes, however, behave in ways that present challenges for both medical professionals and scientists alike. Coatings are then used to help protect and broaden the uses of these electrodes. Developments in electrode coatings could potentially lead to longer-lasting and more reliable deep tissue implants, expanding treatment options for previously untreatable conditions. These coatings are used to help reduce impedance and protect electrodes from deterioration. However, they have not yet been able to be left in vitro for extended periods of time, often limiting use cases of bioelectrodes. For this project, we aim to modify P.PSS, which is a commonly used coating due to its conductive and protective properties in acute cases. By modifying P.PSS with carbon-maxine-based materials, we hope to increase the longevity of electrodes and help them retain conductivity in the chronic, expanding opportunities and potential uses of electrodes. For the preparation of electrode cells, electrodes are coated in either maxine or carbon-based coatings. Electrode coatings are made by Charlita, an undergraduate researcher, and Gabriel, a graduate researcher. Electrodes are then attached in equidistantly spaced triplets in a container of saline to form a cell. Then 7 electrode cells are put together in a set of cells to be taken and tested in parallel. These cells are then connected to a custom printed circuit board, or a PCB. This is seen in image 1. The accelerated aging process is used to help place electrodes under a great amount of stress, so we can see how long it takes for the electrodes to break down, allowing us to determine their lifespan and overall limitations. For this process, electrodes will be submerged constantly in a saline solution. Electrodes are then held at a constant warm temperature around 70 degrees Celsius. Cells are then simultaneously and continuously stimulated with electricity. Then the design of a printed circuit board, or PCB. Originally, cells were tested individually, and these readings were gathered through an oscilloscope. However, this process was tedious and often required interrupting the accelerated aging process for longer periods as well. The PCB was created using CAD, or computer-aided design software like Fusion 360 to design the case, and Eagle, an electronic design automation, or EDA software, to design the layout and the board design. This PCB was created to streamline the testing process, allowing the simultaneous testing of multiple cells at once by connecting each component together. The device has 7 channels with 4 input ports and is shown in image 3. Then for the experimental design of our project. During the accelerated aging process, which helps simulate an in vitro implant, cells are then connected to a custom PCB. This PCB supplies all the cells with power and outputs the cell's readings to a DAC, which communicates this information to the computer. During this time, an oscilloscope is then used to help take voltage readings and will graphically display that information. The information is then transcribed to the computer, which is gathered by Mr. Kick, a data analysis software, which monitors and records the changes in voltage over a period. Data is then gathered from Mr. Kick and exported to MATLAB, where it is graphed and labeled so experimenters can monitor changes in resistance and conductivity over time. These results are shown in our results section, where these graphs represent voltage over time that is flowing through the cells. These values are used to determine whether an electrode cell is working and how well it is still working. The closer the range of values for a voltage minimum maximums, as well as the more consistent the waveform, are good indicators of whether the cell is working or not. For example, we see channels 2 and 3, which have similar ranges and similar waveforms. This would be an example of a good pairing where they're under similar degradation. However, for channels like 1 and 5, the more inconsistent the shape of the waveform and the more inconsistent the range of voltages, the more degraded the cell is, ultimately failing as we see in channel 5. To conclude, the finished PCB allows for simultaneous testing of all 7 cells as shown in the image above. This adaptation to our experimental design will assist in the project by allowing the collection of data with a higher efficiency. These findings support the possibility of improving bioelectrodes using modified bases. However, further testing is required. For our future work, we hope to get some further testing done and increase the duration of the testing, collect more data on the rate of decay, as well as identify a final time before cells are ineffective. And then through the manipulation of these bases, we hope to find the effect on the electrode's performance in the chronic. And then if you'd like to learn more about the carbon Maxine bases, these references would be a great help. They help me begin to understand it. And then you can also go to the QR code and explore more and see exactly what our lab is all about. Thank you for your time and have a great day.